Hi YouTube. So in the last video we learned that if we narrow down our calculations to a quantum scale, what we realize is that the energy comes in discrete packages, and we have finally quantized the energy there. And we have also discovered that the energy is actually n square, pi square, h bar square, or 2m a square. So energy depends on n square and n is an integer, so energy comes in discrete packets. And now here we will take an example of a macroscopic object first to see what happens. So here I have a ball of 500 grams that is confined in a potential box of infinite potential whose distance is x equal to 0 and x equal to 10. Noticeable. Mass of the ball 500 grams. Again, noticeable. So let's apply this formula here. For the ground state first, so E1 will be equal to n is 1. Let me also write down the formula of Planck's constant here. So h bar, since h bar is h over 2 pi, only h will be 6.6 times 10 to the power negative 34 something. And h square will be 43 so let's just write 43, order matters, times 10 to the power negative 68. So my E1 will be h square, that is 43 times 10 to the power negative 68, over 2 times the mass in kilograms, since we are using SI units here, so 0.5 times a square. A is 10 here, so times 100. This will give me 0.43 times 10 to the power negative 68 joules. And if I want to calculate this in electron volts, I simply have to divide this by 1.6 times 10 to the power negative 19. So 0.43 times 10 to the power negative 68 over 1.6 times 10 to the power negative 19. This is in joules. And this will be something close to 0.26 times 10 to the power negative 49 electron volts. Now, we don't have any device that measures the energy of the particle in the order of 10 to the power negative 68 joules or in 10 to the power negative 49 electron volts. We simply don't have. And that's why we usually don't observe the energy of this ball, which is confined at the potential well. And that's why we ignore these values here. Even for the first excited state, all we have to do is put the value of n as 2, and simply this value will become into 4. So at first excited state, 26 times 4, which will be 1.04 times 10 to the power negative 49. Again, not noticeable. Since the order hasn't changed, it's still negative 49. So now you may get it. When we try to observe the energy in this form for macroscopic objects whose measurements, whose mass, and whose lengths are observable by human standards, then you get energy which is very negligible and it doesn't do anything. But now, let's try to calculate the energy for a microscopic object, for example, an electron. Now let's look at a microscopic example. We have an electron that is bound in an infinite potential well of the length very small, 1 angstrom, which is 10 to the power negative 10 meters, and whose mass is simply 9.1 times 10 to the power negative 31 kilos. So my A is 10 to the power negative 10. And a quick fact, if the electron has to go from a bound state to excited state, then the electron will have to absorb a photon for it. So when electron absorbs the photon, it gets energy in order to jump from the lower orbit to higher orbit. In order to go from higher orbit to lower orbit, the electron will eject a photon, since the electron's energy is getting less. So it ejects a photon, and it goes from an excited state to bound state here. So now let's calculate E1 first, which is simply n square, h bar square. So you know the formula, E is n square, h bar square, pi square, over 2m a square. So my E1 will be, since my n is 1 here, it will be simply h square, which is 43 times 10 to the power negative 68, divided by 2 times the mass, which is 18.2 times 10 to the power negative 31, times A, which is 1 angstrom, or 10 to the power negative 10 meters, times 10 to the power negative 10. If I want to solve for this more, then my E1 will become 2.6 times 10 to the power 68, and then this becomes 41. So this becomes 10 to the power negative 18. And again, this is my energy in joules. If I want to calculate this in electron volts, then I simply have to do E1 equals to this thing divided by 1.6 times 10 to the power minus 19, which will simply be equal to close to 1.4 times 10, which is 14 electron volts. This is not an ignorable energy in the first place. 14 electron volts is in fact the binding energy of hydrogen. That is, 14 electron volts is in fact the energy that requires for the hydrogen nucleus to separate itself from the protons and neutrons. So again, at quantum realms, the energies cannot be ignored because you have a very, very low order of mass for the electrons and also the distance between them. Anything you increase, you will have a little bit negligible or a little bit higher amount of or lower amount of energy depending on the values. So I want you to play with these equations yourself. And again, I want you to calculate the value at n equals to 2 and let me know in the comments. If you didn't understand anything, please let me know in the comments again and I will solve the examples for you. If you want more examples, please let me know. Thank you very much for watching. Subscribe for more.